Welcome to the poster presentation about the impact of scaling errors of the thigh and shank segments on musculoskeletal simulation results. Musculoskeletal simulations are widely used in the research community, and they are increasingly used to answer clinical relevant questions. Therefore, accuracy of the simulations, and especially the knowledge of potential errors, is important. The gold standard to create a subject-specific model is by segmenting medical images. However, this approach is time-consuming, expensive, and requires additional knowledge. Therefore, most studies use marker-based scaling approaches to scale a generic model to the participants' anthropometry. Previous studies showed that these approaches include errors of up to plus minus 12.4% of femur length in children with cerebral palsy. These errors come from slightly misplaced markers on the participant or the model and from the participant's standing position. For example, when the anterior, superior iliaca spina and lateral knee markers are used to scale the thigh segment, an increased hip flexion angle decreases the femur length. In this study, we wanted to analyze the impact of scaling errors of thigh and shank segments in a systematic and comprehensive way. To do this, data of a child with cerebral palsy and one typically developing child were retrospectively analyzed. We scaled a generic model to fit the participants' anthropometry based on measurements from MRI. Then we adjusted thigh and shank segments by mimicking a misplaced lateral epicondyle marker. In total, 30 additional models were created, which included altered thigh lengths of plus minus 15%. Subsequently, the reference and all adjusted models and the corresponding gait analysis data were used to run inverse kinematics, followed by inverse dynamics, static optimization by minimizing the sum of squared muscle activations, and joint reaction load analysis with OpenSim. Finally, we compared the waveforms of all these simulation results between the reference and the adjusted models. Also, the root mean square errors were calculated to get a better overview of the impact of the scaling error on each output parameter. Our findings showed maximum errors in joint kinematics of almost 10 degrees for the hip flexion angle. The impact on joint moments was rather small, with a maximum diverge of 0.15 Newton meter per kilogram for the knee flexion moment. Muscle forces varied up to 46%, and the hip joint contact forces were increased by almost 15%. Our findings showed that the impact of scaling errors on simulation results is similar for pathological and typical gait. Scaling errors mainly change the magnitude, but not the shape and function of most analyzed parameters. Our root mean square error plots can and should be used to estimate potential errors due to marker-based scaling approaches in previous and future studies. The full paper got recently published in Gait and Posture and is freely available with this QR code.